Okay, so I'm sorry. First of all, there's still some issues with the microphone. You see, starting of the semester, not everything is working yet. I called the technician, so hopefully he will come during the lecture and maybe you can hear me then better. I'll try my best to make me understandable until there. Then, and if you can't understand me, there's also some spaces more in the front. You can also move a bit more to the front. But I assume it's the best to start a bit and then we'll see. Hopefully soon you can hear me better. My name is Jan Nieuws. I'm here leading the AI for LT group, so artificial intelligence for language technologies. And this is the lecture on neural networks and deep learning. And yeah, I'll try to introduce you to different techniques and methods in deep learning, which are some of the state of the art nowadays, not only in language technologies, but in many other things. And so this should give you a bit of background on like how these techniques work. I guess you all know them nowadays, for example, used in large language models. Of course, always a bit also with the looking at what is the application at the end. What is our plan for today? So one thing is I want to motivate you a bit more why we think this is a super important and interesting lecture. We'll show you a bit where these techniques nowadays are used, neural networks, and therefore like give you a bit of an idea of why this is important. We'll talk to you shortly about the organizational stuff, because I guess you want to know all these things too. And then content-wise today we'll have mainly two bigger parts. The first one is on the history of neural networks. We make a very brief recap on how they were developed, although they are currently very hyped, or maybe by now already the last 10 years. The history goes quite a bit further back, and there's very important developments in there. And then we'll cover a bit the AI basics for today. I assume most of you have listened to Introduction to AI in the bachelor's. Is that true or not? Who has had already an introduction lecture in AI? Okay, yeah, so half of it at least. And who of you has covered neural networks in some lecture before?
Kan ik nog snel,
Ja, zeker.
kan ik nog snel rondvaren wie dat?
Yeah, okay, yeah. So we have to shortly restart and hopefully then we'll see. I'll just talk without the slides a bit because that's important. So therefore, what we'll today cover is we'll do a bit of repetition of the very basic things of neural networks. Because I assume most of you are familiar with that already. So we cover what is a basic feed-forward neural network, what is backpropagation, and so on, so that we can deepen that in the following and then go to more advanced neural networks in the following things. With this, we will come to some examples. Once the system is up again, I can start talking about them already. So I guess the most common use case you currently have accounted neural networks already is in ChatGPT or by now any other system based on large language models. In all these large language models, the core component is in there is a neural network which can somehow you predict the continuation of the words. And that's why we will, of course, also in the later look at that. Well, at the beginning, we'll look at architectures. There we will look like what type of architectures are used in also things like large language models. Then how we're training, we'll especially look at one important thing of large language models is the first thing, the large. So we'll also look at like how you can train efficiently with really large data. And so this is like somehow the most commonly applied thing of where neural networks are nowadays used. That is a nice thing about text. applications, you don't need really slides. I'll come to the next one, which is vision, where I guess it's somehow an advantage if we can also see the applications. One more try.
Ja, ja, das kriege ich schon.
So, I mean, besides generating text nowadays, of course, also generating videos is a more and more commonly used example. I guess most of you have seen things like Sora. Who knows about Sora? Yeah. So, yeah, also in this types of models, the core component inside is a neural network. And therefore, like if you're interested in like developing ideas for all these types of applications, it's essential to really understand how neural networks are working, how they are trained, and that will be the main focus of this type of lecture. See, even more simple techniques are still. Kann ich wieder starten, oder?
Also dieses Jahr kriegen wir inzwischen
Alles.
Wetter nur wahrscheinlich kriegen. Leider ich nicht mehr verpassen kann, sozusagen. Und irgendwo Kleber von
Licht ist schon wieder da. Ah.
Sieht besser aus.
Also,
Wir benutzen sie.
das ist gut, ja. Okay, können Sie mich jetzt besser hören? Okay, sehr gut. Dann würde ich noch eben wieder den Desktop freigeben. Ich denke, yeah, so besides pure text, you see here also what is possible with neural networks. This is like a video generated just by a prompt. And this is also like in the background, of course, mainly a large neural network, which was trained to do things like that. Another use case is things like this one, say can, where it's about controlling robots. So you say something, I spilled a Coke, can you do that? And then you have a model in between which tries to do that. So also like in these ones, we're seeing more and more applications of neural networks, where you do the planning, what to do in order to get the code, and so on. So we're seeing that, yeah, in a quite variety of different applications domains, you nowadays need neural networks, and that is maybe the one very interesting thing about deep learning is like before in all these areas you had very dedicated methods to do all these things, while now we're seeing that there is a basic approach which surprisingly works in very many applications domains. And this basic models behind them will be the focus of this lectures. How we're using it here at KIT is also, so we have the lecture translator, which is there for translating and doing more things about lectures. We're also like all the core components by now are based on neural networks. For this lecture, I didn't use it for live translation because normally I didn't have really students who are interested in having subtitles other than English. However, if you prefer to have subtitles live other than English, please tell us, and we can also provide you with that. What we will do is, now I need the mouse. So to see a bit, so we will use the lecture translator for uploading the videos. What you then do is here with neural networks, what you see is you have a transcript, you have translations, you see different chapters. So this is last year's lectures. You see automatic keywords on what has been presented here. You can see the transcript as well as shorter versions of it, like 90 and 50%. So this is all generated by AI. Of course, hopefully during the lectures, you will learn that you shouldn't blindly trust any AI systems, and we'll cover that. So always take all these types of things with curiosity and be think about that, but hopefully it can help you. What we also have now is that you can ask questions about the lectures. So things like the important question for most students, when is the exam? And that should be then answered based on the transcript. You can even, I think, if you turn on here, video control and ask, what is a neural network? You should be able that the video then also jumps to where this was explained in the lecture. Of course, now it didn't work, but yeah. So this is a tool you can use. It's development at KIT and here, so might not be super fast. And if you know, I'll go on there and try it. I see some of you will be very slow. But if you have time, and I guess normally you don't do it all at the same time, so try it, give us feedback. As I said, it's not a service which is like paid by, so we are doing it in our research. Might not work everything always, but we hope to provide you extra help in doing this. Okay. Then there's, of course, more things where in your daily life you see neural networks. I guess most of you use some type of personal assistant, let it be Alexa or Siri. And nowadays, in a lot of these components, again, like a neural network is somehow a very core concept on that. So in summary, if you think about a lot of these AI agents nowadays called, or AI-based systems, they do some perception, they like get some input, let it be text, audio, video, and then the core thing of how to process that, that is the main change in the last 10 or 15 years, is that it's nearly always a neural network in there, which does the processing and then there's some type of generation afterward. So while there were like dedicated solutions for a lot of these problems beforehand, now we see this one big hammer, which you can nearly always use and get really good results. And that's what will be the core of of this type of lecture to this semester, where we want to look how we can use that in, or what it is, what we need to know, how we can build these systems. And then there might be other lectures where you learn more about how to applying them. We'll mainly focus on how really to build these types of systems. What a neural network is, as I heard you mainly have an idea of it, is like this type of structure. You'll see this type of images very often during the lecture. So what it is like a machine learning model. It is originally inspired by some type of biological neural network. But since then, it has advanced very far. And today, the connection between the biological neural network and the artificial neural network is not really that strong anymore. We will see, especially today and on Thursday, it's mainly some type of, we do matrix multiplications, nonlinear functions on that, and that we do a lot of times. The connection to biologically, at least in what we've seen recently, wasn't like a major, I mean, of course, it's a nice selling point, but the real advantages are how we can efficiently compute these things of things. What you hopefully know already, and where we'll cover today again, is important is that we have this structure, we have different layers. That makes really the model strong. We see the original perceptron was a single model that is somehow quite weak. We have a very simple problem, which it can't solve already. Does anybody know what this simple problem is?
The XOR problem.
Yes, exactly. So the XOR problem, we'll come to that. A very simple task function that it can't be approximated, and that's why you need a more complex structure like that. The important thing is also it's trained, which is a big difference to what has been done there before. Like there you had in AI, you had more rule-based systems where it's more like programming. You say, if this input happens to this input. The nice thing here in machine learning is in general, but of course also for neural networks, is you're not defining when to answer how, but you're giving examples and the model extracts how to answer for new data based on that. And typically it's just like approximating some type of function. So it should, for some input, give you the respective output. What was important and why then the term deep learning, which by now may be outdated again. Now everybody's talking about LLMs, but there it's again deep. So this type of, this idea of deep really like pushes and makes these models more stronger. And here the deep just means that you have many layers. So while initially you had something like here, where you had an input layer, a middle layer, and an output layer, nowadays we are seeing very, very deep layers, like with hundreds of layers on top of each other. And this gives the model the capacity to really approximate interesting functions and be useful in interesting tasks. Where especially like before it was rule-based, in a lot of cases, this wasn't be possible, or with simpler ML, where you have very complex functions to approximate and ambiguities to resolve. If you think about generating text, you need to understand quite a lot, and there are subtle differences. And the input can lead to quite different things on the output. So this is hopefully a bit motivating why this should be a topic where you're interested in, where it's helpful to learn something about. And with this, I would go for the next part, the more organizational stuff. But there, of course, if you have questions, please ask them now already. And also during the lecture, please, it's more interesting for me if I not have to talk all the time. So if you have any questions in between, please try to ask them directly already. And although we're a bit of a bigger group, that is most helpful. So who are we? Yeah, oh, sorry.
Is there a difference in terminology for machine learning and neural networks, or does machine learning use neural networks?
No, the terminology is machine learning is a lot of different methods you can have in machine learning. There's like support vector machines, other types of classifiers, and so on. So machine learning, and one machine learning method is neural networks. So, and that we will cover. That is maybe a bit too extreme, because why this confusion happens is, as I said before, we had typically for applications very different machine learning methods. What is currently the case is that nearly in all applications, neural networks are somehow the state of the art. This is like how you're doing it. So it's a bit like, yeah, there's a lot of different other machine learning methods, but at least at the moment, I would say the by far most important are based on neural networks methods. But in general, machine learning is a wider term, and neural networks is one specific model to do that. Machine learning is, of course, even more. Machine learning is on the one hand the models or the approaches you can do. It's also like how you're learning. We're doing that if you do supervised learning or unsupervised learning and so on. But you can even do the different learnings with neural networks. It's just like one specific type of model doing that. So yeah, I guess you know me by now. So I'll give most of the lectures. I get a lot of support by Tuan and Supriti, who will give some lectures, and especially they'll do the practical parts. So we'll try to combine it in a bit, that there's not always lectures. There's also 6 times during the semester where there's practicals, where you should practically do the thing. So yeah, it's and this will be mainly guided by Tuan and Supriti. How the lecture is this is our rough idea or plan. You know, plans are there to make, but then you'll change them. So I'm not saying that in the end of July exactly the things will happen, but this is the rough plan of how we're doing it. You see, there are several times where on Thursdays there is a holiday, so there you won't have. We have also the break of 1 week. Otherwise, you see the lectures. We plan to have around 19 lectures in total, and then there is like 6 practicals in between. This week we'll start today with introduction, and then maybe a bit surprising, we'll do on Thursday something about more GPUs, because one important thing of current neural networks is you want to do them on large data, and that's why it's important to make them very efficient. And there was a huge boost in the application of neural networks when people started to calculate things on GPU in contrast to before on CPU. And we will want to understand what is happening there, because it's nowadays you have some type of co-design in a way that it's not always that somehow the best neural network, which on any architecture would be the best, is in the end the most interesting one. But when designing a new architecture, you might think it's good to think about what is the hardware it's run on, so that you design your algorithms in a way that they are very efficient on this type of hardware. This is not a hardware lecture, don't worry, but we should get a bit of an idea on how these models are later applied. Again, motivated by, if you remember, it's important to train on data. And if you think about large language models, it's important that they are trained on really, really large data, and you can only do that if you're efficient in order to do that. Then we'll look into different types of architectures. Some of them you might know, like RNNs, CNNs. We'll look at self-attention, state space models, and so on. Then the second part will be more about how to train the models. And then we have a last part, which is more about foundation models, which we're currently seeing, where you train basic models and then you apply them to other tasks. In addition to the lectures, we have the practical sections. You can before look already at the exercise sheets, but you'll have time during the practical to do the exercise sheets. So it's more up to you there. It will be based on Python, so please bring your laptop for this, for the practicals, and then you should, hopefully be able to do these types of exercises yourself, because especially in this type of neural network, I think it's important to get some hands-on experience, and only if you have really like used the models, implemented some stuff, you get a lot better understanding on that. So we don't have dedicated points for them. It's up to you, but I can only advise you to take part in the exams. They help you to really understand that. and then be also able to be good at the exam at the end. I guess you're interested in also how to get your content. I hope you are all registered already to the Ilias course. If you're not registered, please register within the Ilias course. That's how we can reach you. Of course, we hope that everything works always as planned, but things are not always as we planned. So if we need to give you some information, this is the easiest for us. Then we can send an email through Ilias. So please register there. That's also where you get all the slides. At least I try to upload slides before the lecture, so you should be able to download them there before. It's where also the exercises will be put, and we'll have a link to the lecture translator where you can see all the recordings. I'll try to record everything you see. I'm currently recording here, but I cannot promise that no error ever happens. So we had that last year in another lecture that, for example, the audio wasn't recorded or anything like that. Things like that. Good point. Should record. Yes, it records. Okay. So this might happen. So then, of course, you still have maybe some fallback with the slides with some lecture from last year, but out of experience, I can only advise you to come to the lecture and also listen, because here you can do questions. And I guess at least for most students, it's a lot harder to motivate to sit in your home and watch the videos than coming here. But you're master students, you're old enough. So of course, it's up to you how you do your learning. As I said, also, we try to give you additional support on the lecture translator with the transcripts and so on. Try to use them if they're helpful. And some people, for example, in other lectures complained that there's too few text on the slides. That's because I want you to listen to me and not read all the slides. So it might be helpful to read something in the transcripts. But yeah, I guess you by now know how to best do your learning. I guess some of you might still be also interested in when to do the exam. This is the current exam date in September. It's far away, but hopefully you also know that it might not be best to start learning on the 10th of September, but maybe to start preparing a bit earlier. The exam is early in the morning, so one morning you have to get up early. The duration is 1 hour, is with preparation and so on. So we have a 2-hour slot, but there's a 1-hour exam, and that should be. So it's in the end, you see the bigger crowd, so it will be a written exam. You'll get the questions in German and in English, and you can answer in the language you prefer. However, it needs to be somehow understandable. So if you switch word by word between German and English, we might no longer understand things. Yes, and maybe the last for the organization. So content-wise, to get more interesting again, what we have is, as I said, so today is more introduction. Then we talk about architectures, and then we will have more on the how we can learn these architectures. Of course, they are not completely independent, but the first ones will more concentrate on how we can define a neural network, the same, how we can train it. And then the last thing will be more on what is recently the high topics, like how these foundational models are built and what are foundational models. Good. So before we are coming to the history, any questions? Yes.
Will the exercises also be recorded, or just a lecture?
Last year, I think we recorded the lecture, the exercises also. So we'll also try to record the good. So in generally, how machine learning, or no, not machine learning, that's no wrong. How AI systems are built is people started with what they know in the 60s is about building rules and having rule-based systems. We see there were first artificial neural networks already before that, but that was some of the dominant approach. But for a lot of tasks, people see that just defining everything is too difficult and not really possible. And that's why people then looked into more learning things. So machine learning came more common, and we could address a lot more problems with that. People started with what was called more the statistical models, which was very simple classifiers, which calculate statistics on the data, and then you do some prediction based on that. And then more like around 15 years ago, really these type of neural network-based approaches for a lot of wide range of applications really hit, and we could build state of the art. Again, we'll see before 2010, a lot of things on neural networks has been done, but because of data, because of computational power, and because of things weren't as fast developed, they typically weren't like somehow the best for the individual task. That changes there. And then what we're recently seeing is then first we had one architecture, but you had different models doing several tasks. So you had one model or maybe like one type of neural network, which is good to do machine translation or speech recognition or visual perception. But these were all individual models which were dedicated for each of these tasks. The interesting thing with now foundation models and large language models is that then people started to build one model which can do a lot of these tasks. And that is in one way very important, because often it's hard to learn everything from the start with the data specific to the one task. While with foundation model, you once learn a lot of general understanding of what the model has seen, and then it's more easily, and with fewer data, you can learn things for specific tasks. And that again was a second, important step to really get this thing very good. And if we are looking directly at neural networks, there was a first type of perceptron, which was in 1943. That was like, the first type of neuron, and that was not being learned. So this was more just being programmed. So you hand define which features you take, but then you already have this weighted function. So you take some weights, you multiply them with your input. If the value is bigger than 0, then you classify it as 1, and otherwise as -1. That already goes very, very similar to how current neural networks look like. Then there was the first type of neural network, which was a Rosenblatt perceptron, where you were able to learn these type of neural networks. So now no longer the weights we had before were like defined, but you have the learning. You have here your xn is your training data, and then you have your yn is your label, and then you're learning the weights by minimizing some type of loss here. And this was like giving a first hype, you see, beginning of the 60s, quite a long time ago, where people started to get interested. However, then there was this first discouraging result, which was by Minsky and Pepper, which was like a very simple problem, like the XOR. So you have two inputs, and the output should be the XOR of it. So if both are 0 or both are 1, the output should be 1. If they are different, the output should be 0. Very simple problem. And with this type of perceptron, you cannot solve that, which is, of course, a bit like sad, because if you can't do that very simple task, how do you want to address more and more challenging tasks in there? So based on that, there was, again, like you always see, there's a hype, and then people find some problems, and then most people go away again, do other things. However, at some point, one interesting solutions came to that, and that was a multi-layer perception. You see here an early image of that, and that already looks more similar to what current neural networks is. And the main idea was that you can really train, that you can now use not one single neuron, but you stack them in different layers. And then you can solve problems like the XOR and even more complex ones like that. However, there wasn't directly how you can really efficiently train that. And that is another important thing we'll talk about today, is like the backpropagation. So that is essential to train nowadays large neural networks, is like, how do you find the right parameters? So if you think about it, maybe you've seen one of the announcement of the large language models. They're talking about, oh, this is a 9 billion parameter model. This is a 70 billion parameter. This is even 400 billion. So if you think about it, if you have to define 400 billion parameters, you can't do that by hand. You can say, oh, this value should be 0.2 and this should be minus 1.5 and so on. But you need an algorithm which from the data extracts what are good values. And for that one, we need backpropagation, where we can efficiently calculate the gradient. And then we can do what is called gradient descent. So the main idea is you try to improve your loss function in every step. And so with backpropagation, it was possible to do gradient-based learning, meaning we're step by step improving our model. We can just start with a random initialization. We take a random model, which of course performs quite bad, but then step by step, the model gets better and better. And so in the end, we'll then hopefully have some type of good model. There has been previous work in this area on optimization, but in backpropagation, it was like in 82, it was like the first time really applied to neural networks, and you were able to train the whole model. This is one also very interesting thing of neural networks. Before you had often modular structures, and then you optimize each part individual. With backpropagation, you can like tune all your parameters in there to have the best overall performance. And the only thing you have to do is somehow at the end measure how big your error was and then backpropagate things. And then more and more complex structures or like type of networks came on. One example is like time-delayed neural networks, now which are called convolutional neural networks, where you not only have a fixed input size, you'll see that in architecture, but you can have variable size input, because a lot of signals we are not having like an input which is always 100 inputs. If you think about text, a sentence can have different number of words. And if you have audio, the length is also variable. So you have to have the ability to handle this type of variable input. And that is, for example, one way of doing it. And then, I mean, of course, this is a bit selected. There's a lot of other things. We'll talk about LSTMs, for example, RNNs, which are also a good way of handling this thing, which came in the mid of the 90s. One definitely more recent important step was that people then ported this from CPU to GPU, which just means we can do a lot more calculations and you can efficiently train these types of models. First, so the one step is in 2007, CUDA was published, where the first idea was that you no longer only can do graphics calculations on your GPU, but there's a general library where you can also do other types of calculations. And then this was applied to machine learning in 2009, and that really like speeded up things heavily. And if you see nowadays, the biggest company of GPUs, NVIDIA, they're mainly not used anymore for gaming, where they were designed for, but training neural networks is an essential part of that. And that's why nowadays they're not only in your home computer for playing, but they are large clusters and computation centers where they're mainly just GPUs where you can do this type of calculation. So that is somehow important, again, because if you really want to benefit from neural networks, is you can process a lot of data and then you can extract information from that. And therefore, you need this type of efficient computation. And then these types of models were successfully applied in very different domains. Maybe one of the first was in vision, 2011, there were, and 12, there were like models which could beat state-of-the-art approaches, where a purely neural network-based approach was better than a model which uses a different machine learning types of models applied to this task, dedicated, developed for this task, but they couldn't generalize as good. And then this DenNet and AlexNet, for example, came out and lead to some of the best performance. In language, then, for example, in 2015, there was an important step where one new type of architecture, which we'll cover in 2 weeks, the so-called attention, was introduced, which allowed it to better handle like text, which focused on some part of your input. And again, then also like led, for example, for this type of best type of performance, in this case, applied to machine translation. And then after like more supervised training, the next question was, how can we use more data? And there the idea of like self-supervised training is essential, so that you no longer need only with data where you have labels, where you know this is the right answer and this is the right answer. Because this is very often very difficult to get. I mean, you need a human who says this is right, this is wrong, and so on. And if this is your only data you can train, it's expensive. And that's why in different applications, here from text and audio, for example, people looked into self-supervised data, where the main idea is you take some data, which is just there, text, vision, audio data, you corrupted it, for example, in some type, and then you predict what was there originally. So you don't need a human to label it. You do it the inverse one. You create an artificial task. And if this artificial task is helpful, you have huge amounts of data where you can train your neural networks. Good. So this was a short, brief walk through the history of AI, or the history of neural networks better. And then for the second part of today, I will talk about a bit of like AI basics. And then you see some learning scenarios. We talked already about, mentioned supervised and semi-supervised learning and so on. Then we look at the perceptron, the multi-layer perceptron, and then especially at backpropagation. Do you have any questions about that? Good. So if you think about how are generally AI-based methods developed, I thought you already started at the beginning more with like rule-based methods, where you define rules of how to do that. So, for example, if you have this task of like classifying images with as animals, or if you have a text where you need to translate from English to German, it would be you define a rule. You say, oh, if you have in English the word I, you should translate it to ich in German. And if you have like in English, you have to translate to Liebe. But you see that even in this very simple example, it's getting complicated. When do you have to translate things how? When do you have to change the sentence structure? If you look at the images, what is really a difference between a cat and a dog? I mean, it's not easy to describe that there's the one feature which you can easily calculate where you say, oh, if you see this type of feature, then it's a cat. And if you see this type of feature, it's a dog. You, I guess, are all quite good at identifying whether it's a cat or a dog. But like giving a rule, like if this happens, it's a dog. If this happens, it's a cat. It's typically very complicated. And that's why then people looked into more machine learning based methods, where instead of like defining by hand what is right, what you do is you give examples, and then you let the model learn its own parameters, for example, in neural networks, like how to distinguish them. So the difference is you give him 3 examples, in reality, of course, more, like saying the top one is a cat, the middle one is a dog, then you have a dino, for example, and then you give it a different image, and you ask him what is now the most probable one. And of course, with 3, that won't work very well. But in general, that is the idea of machine learning, so that you no longer have the task to identify these features are important, this is what I need to do, and these others might not be, but you try to have an algorithm which automatically identifies that, what is important about identifying a dog from a cat, and so on. And if you're doing that, of course, as in all machine learning, also in neural networks, it's then very essential to have the right split, because you're not interested in like learning by heart and just being good at identifying these three images. I mean, that is an easy task if you see the same image again, but you can classify it again as a dog. The interesting thing you're interested in is doing the generalization and being good at other images of dogs. That's why you need to do this type of split. So typically you have some what we refer to as training data, where you optimize all your parameters, where you learn how to do that. Then you might have some development data if you have hyperparameters to train that. And what you're then really interested in is how good is the model on unseen data, because that is typically the realistic scenario. We are not interested in how good have we learned everything by heart. We are interested in how good can we solve new tasks, and that you can simulate by having some type of data not in your training and then having that in the testing. While in traditional neural networks, this is quite easy and straightforward. You have your set, you define something as your test set, training set, you train on that, you then be very precise and make sure that your test data is different, and then you're testing. In what we're seeing currently with foundation models and large language models, these get really complicated. And this is why you see more and more that maybe some performance is overestimated of current models, because there you no longer know what they're really trained on. If you think about the large language models, what they mainly do is they dump the internet and train on the internet. And nobody really knows what is all in your training data. So it's really difficult to find data which the model hasn't been trained on. So yeah, this type of evaluation, benchmarking is still somehow an open question in order how to do it best. Good, so this was the general idea of how we're doing machine learning, how we train the models. There is now different ways of doing that, and we'll refer to that as a learning scenario. So the most common thing we will do here is just supervised learning. So what does that mean? So imagine you want to build an AI system which predicts the grades of exam questions. Don't worry, we won't do that. We'll do that ourselves. But if you want to build this type of model, what you need is you have your input is like pairs of questions and answers. And then your labels are points. So for this answer, the student got this type of points and so on. And then you can train your model. That's your training set and your test set. You again give a question and answer pair. And then your label is the number of points you need to predict. You already see here what is your labels and how your data looks like depends on the task. If you want to build a model which solves exam questions, it's a different thing. Then your input is the question and the label is your is the answer. So what is your label really depends always on what type of task you're addressing. But in a supervised task, the important thing is the label is what you want to predict, and that is in there. So that is what people refer to as supervised learning. Another thing you can do is unsupervised learning. In this case, you're trying not to have labeled data again, because it's expensive. You have to collect all the human labels of all the things. So in this case, what you have is you have a question and the answer, and then you're just trying to, for example, cluster them here. So data clustering is one example of unsupervised learning, and which means then that you don't have how many points it is, but the hope is maybe that everything in one cluster should have the same number of points, because the model has learned to make similar things together. So hopefully you'll learn something that, yeah, that in one cluster things should get similar points. It's not typically unsupervised learning, things are not as helpful, but you have more data and you can better train on them. Then we have self-supervised learning, where, as I said, the idea is oh, we only have unsupervised data, but now we create an artificial task. We do self-supervision. So we create the task ourselves where we have the input and the output. For example, in this scenario, that could be, we have only question and answers. And what we now do is we are creating a task out of that. By giving the question, the model should learn the answer. So the self-supervised task is generating the answer based on the question. The nice thing is normally you have a lot more data for that. It's the same data you need here than you need for the unsupervised task. But you're learning it in a supervised fashion. You can learn the same methods we have for supervised learning. And then you can think how this can be useful. Because you can then, for example, look how probable this answer is. And hopefully there's a good correlation. If the answer is more probable by the model, most of your answers are more correct, then at least the model has learned. And then you should give more points to that, for example. This is the idea of self-supervised learning, that you're not have labeled data, but you take unlabeled data and cast it into a supervised learning problem. Then there's also, of course, combinations of that. You can, for example, have semi-supervised learning, where there is you have question and answers and grades you have for some, but not for all. What you then maybe can do is some type of mix of unsupervised and supervised learning. You learn that, oh, if these are similar and for most of them are negative, then maybe all of them should be negative and so on. So there are dedicated methods for doing self-supervised learning. And finally, which we only cover roughly here and later, is you can do reinforcement learning, where in this case, you wouldn't have, for example, exact grades for each question, but you would only know the final grade of the full exam with all the questions. So you don't know how many points each question will get, but you have this reward which tells you, oh, the overall question got a 1, then you know, oh, most answers should be correct. And if there was like a 5, then most questions will be wrong. You have to learn, of course, which one were right and which one were wrong, because not all of them were right or wrong, but you have a bit of an idea on that. Good. Any more questions on that? Yes, and then we're coming to the core of these lectures. So typically, neural networks are applied to supervised learning. You see there are some networks which can also be used for unsupervised learning. Self-supervised learning, as we've seen, is in the end for the model the same thing as supervised learning. It's more like trained on the different tasks. And of course, they're also used in reinforcement learning, but let's say at least the most important thing in this lecture will be supervised learning tasks, where we have some input, we have then our neural network and need to predict it. And of course, there are a lot of other approaches. So there is not only like neural networks or deep learning for that, there is support vector machines, there is naive Bayes classifiers and a lot of others. We won't cover them here. We're really focused on neural networks. Or, I mean, there now it's more difficult to differentiate what is deep learning, what is neural network. Neural network is maybe the model, the deep learning is the general approach. And as you normally, this type of network, you wouldn't call a deep network, so it has to have a bit bigger size. Good. Any more questions? Good. Then let's start with the basic thing of a neural network. The basic component, that is what is here shown, the perceptron. What is the perceptron? So what it has is these components. So we start with the input. So it has input features x1 to xn. This is already very important. It's always fixed. So you always, like, if you have one specific neuron, and it always has n inputs. So you have one neuron which maybe can handle 5, another can handle 6, and so on. But one specific has to have always the same thing. That's important. That's why, for example, it's more difficult to handle variable length input. It cannot that you sometimes give input to 3 neurons, and sometimes you get 5, and sometimes you get, I don't know how many. So it always has a fixed size. And then you have these weights, which are assigned to each input. So you have W1, W0 to Wn, which give you the weights to that. Typically, you have a bias, which just means that your input 0 is always 1, and then you can multiply. Then you build the weighted sum of that. And then you have here an activation function, which is a nonlinear function, which transforms this input to another one. Typical ones are, for example, sigmoid and tangent hyperbolicus. And that will then give you the output, which you might, if it's the full model, you can compare the output to your reference label y that you have. How do you calculate that? So we calculate k as a weighted sum from 1 to n wi times xi. So it's just the weighted sum, and then you apply the nonlinear function on top of it. This is the normal type of calculation. This is also maybe how you would implement that if you're running it on a CPU. You would do nicely a for loop, which goes over it, and that's it. Nowadays, it's also always good to have more a matrix-based view. So what it means in this case is you have your weight vector W, you have your input vector X, then you just do the product of both of that. That will give you K, and then you apply the nonlinear function to it to get that. What does that mean now for this type of perceptron? On a graphical interpretation, as I said, you have your weight vector W, and you have your input vector X, and then you just multiply them. So if you multiply them, what is it then happen is that this blue scalar, like the length of this thing, is what you're representing. So that is the input. And that's why, like a normal perceptron, very nicely separates the whole space here for easier visualization in 2D into two parts. So you have the blue one, which is positive, and here the results will be negative. So if your X is somewhere in the green one, the product of W and X will be negative. And if the value of X and Y is positive, the X has to be somewhere in the blue part. So of course, extend it. And that is somehow showing you that this is like, that's why they are called linearable separable. So you always in the end have this linear line which differentiates between positive and negative outcomes. And this is also the reason why simple perceptron have the problem, because the simple XOR problem is not linearly separable. So if you have the XOR, you have x1, x2, and if they are different, it's 1. If they're the same, it's 0. So if you mark that here, you have the 2 blue spots and the 2 green spots. And in order to build now a simple perceptron which can solve that, as we've seen before, we need to somehow draw this line so that all blue spots are on the one side, one half, and all green spots are on the other half. And if you now see that, it's nicely seen, you cannot draw the line. Any line you draw here, there will be on one side both the green point and the blue point. So if you draw somehow the line something like this, then this blue will be on the other hand, but the other blue will be on the other side. So it's not possible to draw one line so that all blue spots are on the one side and all green points are on the other side. And that's showing you that this type of problem you cannot solve with a simple perceptron. So yeah, this somehow shows that, yeah, this type of method is maybe not as good just by itself. And as I said, this was a bit the important step when people, the first, which led to the first winter of AI, is people saw, oh, this is a very nice technique. You can nicely spot it, you can classify, you can learn the W's, but you can only learn models where all the labels are on the one side and the other labels on the other side. If they are more mixed, like in the XOR problem, it's no longer possible, because in this case, you cannot draw this linear line. So you can only learn functions with linear separable features in them. Any questions to that? Good. Then, but as you all know, there wasn't the end of neural networks. We're still now using them all. So somebody had to come up with something to make them more powerful. And the idea is somehow quite straightforward. One of these units are not very powerful. But if we combine these now into a larger network, they get very, very powerful. So what you have to do is, instead of having only one neuron, which takes the input and then produces the output, you combine them. So in the simple case, you have 4 input neurons now, then you have here 3 hidden ones, and they are all connected. So all input units are connected to all hidden units. So normally you have fully connected layer, which means all inputs to one layer are connected to all output. And then you have a second layer, which is like connected from the input, for example, to the output. This is like a minimal multi-layer perceptron where we have the input, the hidden, and the output unit. And we have these weighted connections. So each of these units is now what we had before. So each of them creates a weighted sum. Then it does the activation function and then has an output, and then the output is propagated to the next one. This is then the input for the next layer. So what it means, if you think about, if you compare it to the last picture, here you have now the weights on all the edges. So here between the first and the second layer, you have 4 times 3 weights, so 12 weights in here, connecting all input with all hidden, and you have 3 times 2, so 6 weights between the hidden and the output ones. And that is like your parameters that you have to learn. And with this type of architecture now, that you're no longer having just like a simple unit, but many, you can solve very, very complex tasks. And what is especially interesting, what we'll see is, if you look at these hidden representations, we are calling that, so the activations, they can learn other types of representations of the data, which are hopefully often helpful and can be used for other tasks. So that is very important in these types of networks, that these representations you learn in between, so the activation at that time, they can be very helpful, and they extract mainly what is important in there. If we are looking at the calculation, so first it's very similar. You're not just building now only one weighted sum, but you now have several weighted sums for each of your hidden units, and then you apply your activation again. If you're doing that here, you can do it either the same. Now, if you're going to GPUs, the nice thing is you can do that in parallel. So all the calculations of all k is just the matrix multiplication. So now your Wji is a matrix, and then you have your x here, and you can do your calculation. And now you already see that in neural networks, there is a lot of these types of matrix multiplications. We have always, when you calculate the feed-forward neural network, you have to calculate these types of matrix multiplication, showing that if we can do efficient matrix multiplication, that might be very helpful, because we have to do that very oftentimes. As I said, typically we're not having only like one type of layer, but many, so you have to do a lot of these calculations. And if you can do that efficient, that is helpful. And we're seeing GPUs, the nice thing is we don't have to do that step by step. We don't have to iterate through all of them, but we're having different cores taking over some part of these types of calculations. After that, we'll then have different activation functions. So now you get your input, and then you're putting into it through a nonlinear function. And that is very important that it's nonlinear, and we'll come to why. So typically these things are, for example, the sigmoid. So 1, divided by 1 plus e to the power of minus x, where you see here, you have a smooth function, which you can calculate all the tangent hyperbolicus. There's also things like ReLU, where, for example, here it's 0 and then it's x, or ILU, so a different version of that. Most important, as I said, is like something sigmoid and tangent hyperbolicus, which I trained. And I hope you now have a bit of a question: why should I use a nonlinear function in there? Why is it not enough to just do like this type of weighted sum, and that should work? That is nicely shown if you look at the matrix-based approach. So if you have here the two layer, just assume we don't have a nonlinear function in the hidden layer here. And this is just like the weighted sum of all the inputs. And then this is like the weighted sum of all the hidden states. What is then? So in order to calculate O, what you do is you first take your x, you multiply it by here your weights, W1. This will give you K, so the hidden states here. And then you multiply it by another matrix, and you get your outputs. Do you see any idea why this might not be the best model and why you want to have a nonlinear thing in there? Yes?
You could just multiply the matrices first, and then you're back into the same complement, just one matrix.
Yes, that is. So if you have this type of formulation to calculate that, you can, instead of calculating first W1 times X, you can first calculate W2 times W1. And then you get a matrix W dash. And so your neural network is then W dash times X. What does it mean? In the end, we have again just one single neuron, which is just like the one, or like several outputs maybe, but one single layer. And we learned a single layer is not very helpful, because single layer, you can only do linear separable problems. So if we don't put in there our nonlinearity in between, it means we don't have to care if we have 100, 200, or 5,000 layers. In the end, it's just like it can be squashed all into one single layer. That's why it's important to have the nonlinearity in there, because if you have that in between, you cannot do that anymore. Then the order of how you calculate it is important, and you get different results, and then it's really helpful to have many layers. Is that somehow clear? Yeah. Then we can do the next step. So if you have your output, the question is, how do we train these models? And there we do with the error function. So we are not, important thing we need to know is what should be the output. We'll call that maybe Y here. So you need to know this is the right type of output that we want to have. And then you calculate first your output, and you compare your output to your Y, and the error function measures how big your difference is. So the easiest thing is, for example, something like the mean square error. You just calculate the error on each dimension and sum up the squares in order to tell you how wrong you are. You can also do something like cross entropy. We'll see that later. But in general, you need some type of measure which tells you, oh, this output and this reference, how different are they? Because what you want to learn now, of course, is a model which makes them most similar to each other. So a good error function should be somehow helpful and be meaningful in this type of thing. Again, if you're having the square error, you just take the two vectors, you do the difference and square them, and that will tell you how wrong you are. And then you can now train the model with gradient descent. So as I said, so the starting point is you just do a random model, which will be really bad, will predict very bad things. But the idea is now you measure the error. And if you can do backpropagation, you have like the error independent, dependent on your weight. So what you now know, if you're currently on the green spot, this is calculating your error here that you know, but this is not yet very helpful. What you also need to know is you need to calculate the gradient. which should show in this direction or this direction. Because then you know, if you have the gradient, you know now, oh, maybe I should go into this direction because there my error goes down, because that's what you want to do. You want to reach a point where your error is low. Of course, things are difficult. It's already seen here in the very simple case. If you do it by default, you'll end up here, which is a minimum, which is, of course, maybe not the best because you're not ending here. So there's a lot of things you have to consider in order to work it, but you always have to deal with that. So you don't know the whole function. You don't know like what is the optimal solution everywhere, but what you're trying to find is like somehow a good solution where you have reasonable good performance in there. And then you do is by calculating the derivation, and then you're going one step in the opposite direction like here, and like step by step, you're walking down here and hopefully ending here. Hopefully, of course, in the end, you would even end up here. And yeah, that is a normal gradient descent where, so you're now nearly able to train your model. There's one last thing which it might be challenging. What didn't I explain? The step size is, yeah, of course, I mean, that is the important thing. So you want, if you do too small, you're just ending up here. If you're too big, you're just walking randomly around. So you want to later have a bit of a good step size to end up here. We'll talk about that maybe later. There's also one thing which I just assumed. Maybe you all know how it works, but yeah.
Where to start?
Yes, that is random, yes. But can we just go? How do we know where to go?
We don't know the gradient, yes.
Yes, exactly. So we need to somehow calculate this type of gradient, and we need to calculate it for every W. So for each weight, we need to know in which direction we should change it. So you need to have your gradient with respect to all the weights in order to go then in the correct direction. And that is now the question which we will cover in like the last quarter of an hour here. That's called backpropagation. We'll shortly see why. But the main idea is in order to do gradient descent, and I mean, it's a very intuitive and successful like method of optimizing your parameters. So you just look where I can minimize the error, and then I go always in this direction. It's somehow very intuitive. The question is, how can I do it? And for example, in the original perceptron, where we just had, if it's above 0, it's +1. If it's below 0, it's -1. It's not possible. So you have to have an activation function where you can calculate, at least at most positions, a derivation, because otherwise this learning is not possible. So you cannot take any type of activation function, but you need a reasonably good one. So how do we do that? So you calculate your derivation with backpropagation, and the way it's doing it is we're doing a forward pass, then we're calculating the error. There we have our error function, and then we're backpropagating. That's why it's backpropagation. We are backpropagating the error. We're calculating each weight in here, what is the contribution it has to the error. And in order to do that, all functions in here, so the weighted sum, the activation, and so on, we need to be able to calculate the derivative. And so that we can calculate each contribution to the overall error in order to do that. And yes, that's what we want to do now. So let's again have a look at a very, very simple neural network. So we have CS3 inputs, for example, that's in blue our X. They are multiplied with our weight matrix. Then we are getting to our K, which is our hidden state. Then we have, based on that, then we apply an activation function to that, which is then results in the output O. And based on the output O, we calculate our error, which is our error function. So the first thing we are doing is we are calculating our forward pass. So we are calculating our error. That is the first step, meaning we are giving X, and then we are calculating K of W and X. So this one depends on X. Then we are calculating the output based on K, and then we are calculating the error based on O, which means you can write it either this way or this way, like you apply these three functions, one after the other, always to the output. And all these functions we should know by now. So the first thing is the forward pass. So k of w and x is just the sum here of w ej times xj. I mean, the k j is just ki is just the sum over all the inputs before. And of course, the weights you're using here depends on your input and your output, and that's all the steps we have to do. Based on that, then we're doing our activation function. Again, this should now be an activation function that is differentiable. And for example, here the sigmoid function, which we can apply. And that will give us then our output. And then finally, what we're doing is we're calculating our error. And the error, of course, I shortened here a bit to make it no longer. The error, of course, depends not only on the output, but also on the label, but this is fixed for now. So what we're doing here is just we're doing the weighted sum over all the, the mean square error. So you do the difference between the label and the output, square it, and then you have the sum of all. That is a forward pass. Now, the nice thing is, in over it might be a complex function, but each step here is a very quite simple function where you can even calculate your derivation. And then we can use the chain rule and therefore also calculate the overall derivation quite easy. So what we're interested is we're wanting to know the error here of the whole function. So the application of all the one based on our weight here, because this weight we want to change. Then we can do the chain rule, which means we can calculate the error of the derivation of the error with respect to the output, then the derivation of the output with respect to k, and then the derivation of k with respect to the weight. So I'll do that step by step. So the first one is here, the first term. So the error, the derivation of the error with respect to the output is we want to have this one, and we want to calculate the derivation with respect to OI. It means most of the terms here, all except the one with I, is a constant, so they just fall apart. And then for that one, we have to do the derivation, which is then minus 2 divided by n ye minus OE. So this is just the derivation of this function with respect to OE, because most of the terms are constant, they fall apart, and then you have only OI. Then you have here, like if you want to have x squared derivative, is 2 times x, that's here the 2 times, and then the minus is coming because here the inner derivation is minus 1, and that should be your whole derivation for that. So more like standard derivation, which you hopefully have, for example, done in high school already. Then the next one, is a bit more complicated. I wouldn't know it directly by heart. So if you have a sigmoid function, but luckily the derivation of the sigmoid function is also not too complicated. It's just the sigmoid function times 1 minus the sigmoid function. And so here you see already, so the derivation of your activation function is very important. It has an important influence on how you learn. So it has to be high enough that you're not learning. So a well-designed or well-selected activation function is very important to do the learning. And this is, for example, one of them. And then, here it's getting very simple again. If you now do the derivation of ki with respect to double ij, all terms except of j are constant. So the derivation is 0. So it's just like the derivation of wij xj with respect to xj. That's a linear function. So the derivation is just xj. And that's all. So we have now the individual components here of each part. And now we just can multiply them to get the overall derivation. So that's why, so the overall derivation is then the product of that. So with that one, we know now here for this wij, or for this one or this one, we calculate, or we have calculated the contribution to the overall error, and then can update these weights later. Now you also see why it's called backpropagation, because we are going now from the back where we calculated the error. We went step by step back to calculate derivation of all our input, of all our weights here. Is that somehow clear? Then typically we're doing one more thing. We are also calculating the derivation not with respect to wij, but with respect to xj. The nice thing is very similar, it's only the last term is different here. And so it's not xj, but wij. Now the question is, why are we doing that? And why do we want to have the derivation with respect to xj? Because xj we can't change. I mean, it's the input. You cannot change your weights, but you cannot change your input. That's what you get as input. So why would we be interested in having the derivation here?
Able to improve the bias.
There would be, yes, but normally that's not necessary. You can keep your bias fixed because you can do the same thing by just the weights connected to the bias. But yeah, for this type of network, it's not necessary, but you think of this network somehow different. And yeah.
It's kind of a generative model then. We can generate the new input.
Okay, now you're far to the field. Yes, that is true. You can investigate that, and you can also see how this one contributes to your output. So there's a lot of interesting applications, but it's even useful for very simple classifications. Yes.
We know how sensitive the model is for input changes.
It's not, so maybe, yeah, maybe the picture is irritating you. Yeah, I mean, that is the understanding. So often you're not having one layer, but you now have several layers. So the input here is just the output from the previous layer. And if there is input here, maybe that's why maybe you couldn't come to that because then of course it's not it. But if you now imagine there's one layer below that, then you can't calculate the error of this layer. You can only calculate the error of the top layer. What you then have to do is backpropagate the error from the top here down, and then further down to the weights which are below that. And therefore, if you have once the error here, that's again the starting point. You have the error of the output of this type of layer, and then you can propagate the error here further. That's why you need the x, the error with respect to the x, because this error, this derivation then, you can backpropagate in this network, which might be below here, and then change the weights in this type of network here. So you don't need that if the x is really your input, so the last layer. But if you think of this as a stacked layer with many, and the x is just the input to the current layer, but then also the output of the previous layer, it's how you calculate the contribution to the error here, and you backpropagate it further. So it's necessary in order to backpropagate the errors also for lower layers below that. Good. So to summarize that, so what we hopefully have understand today, and which is our starting point, on which we will do like more advanced networks before, is the multi-layer perceptron. And this is our feed-forward neural network. This is all like synonyms for that. So what this is like each node here is somehow a perceptron. So it does a weighted sum, and it does then the activation function. And the edges are the connections. Typically, we have full connections, meaning within a layer. So all input layers are connected to the next layer and so on. There's no connections from the first to the last or so. You only have always connections from one layer to the next. There might later be more advanced architecture where it's different, but first start with a simple thing. And then we're training it. We saw it before. We do the forward pass where we calculate the error at the end. Then we measure the error with, for example, mean square error. Then we do the backward pass to calculate our contribution to the error. And then with this gradient, we can update the weights, and then we can do it again and again and again. And that's how these types of networks are trained. So to summarize the whole lecture, this is a bit what we covered today. We looked into why neural networks might be important. We looked into like the history of neural networks and some AI basics. You should remember like the different types of learning techniques we have. What is a perceptron? What is the main challenge of a perceptron? What is a multi-layer perceptron? And how you can train it using backpropagation. Do you have any more questions? Yeah. Oh, yeah.
So this is the lectures except for the ones that are recorded on the book.
I mean, yeah, I mean, there is the good, like the deep learning book. We can put that, I think, on the website. There's, for some slides, I put some papers. If there's directly a paper, you can see that. And yeah, we can put like one additional book on the thing. It's not exactly what we're doing here, but it should give you a bit of an overview on deep learning in general. Yeah. And thanks a lot, and see you again on Thursday.